Welcome everybody to the Saturn workshop. We're going to be talking all about machine learning on big data with Dask, and we have a very nice festive holiday theme as well. Actually, you can't even see my sweater. I need to turn this down. So this is a big data Christmas sweater, in case anybody didn't notice. So I think it's very appropriate for what we're doing here today. Okay, so this title is all about hopefully something that a lot of us have encountered before, which is getting memory errors when trying to run machine learning within Python. And so I want to give a really good, just like an introduction into that. You know, the assumption is that we're assuming a lot of people here have a lot of experience already with machine learning, maybe using scikit-learn in Python, but then might be kind of encountering some challenges with larger data sets. And that's kind of like our starting point here. So this is the kind of tried and true machine learning world within Python, right? It's the PyData ecosystem, as we like to call it. And this is like pandas, NumPy, scikit-learn. There's a few other projects, any kind of visualization libraries you might use, and then all kind of wrapped within Jupyter notebooks, whether it's JupyterLab and such. And so these tools are really tried and true. They're tools that data scientists use every day. They're really mature, have been around for years, and are kind of built into a lot of places. The challenges with some of these tools, though, is that they were really built in this kind of like single core in-memory type paradigm. So like when you have a file you want to load into pandas, you got to have enough memory on your machine to kind of hold that full data set, and then it's kind of churning on one core. And that's when we potentially might start to get challenges. But let's just go through a story real quick of like where we have these tools, we've learned them, ready to go, and are like super excited to go ahead and like analyze all the data that is thrown our way. And I'm hoping that this story hits a little close to home for some people here. I know from the survey that we gave in the Slack channel, people did experience some challenges with data sizes. So let's go with this. You can load some CSV file. It loads perfectly fine into pandas. You got a few rows, and then you do whatever analysis you want. You kind of train some models, but then maybe a bigger data set comes around, or maybe you started off with like a sample of the data. So then you're ready to like kind of move forward, increase your data sizes and such. And so you go ahead and try to load that bigger data set, right? And then this is what happens, is this kind of dreaded memory error. And that's kind of the title that we gave for this workshop anyway, because this is something that's happened to me several times. I'm not hoping it happened to you. Well, I'm hoping you're here to try to solve the fact that it's happening, but this is that dreaded error that always happens. So like the best case, maybe your Jupyter kernel dies and you kind of have to restart it and then sample it. Worst case, your whole machine gets like all messed up and you got to like restart your computer. But that's a challenge there, right? So let's say we do get more RAM, right? My computer has 16 gigs of RAM. Let's say I buy a new one with 30 gigs, or get some machine on the cloud with 30, 60 gigs. There's still challenges here. So like you can get to the point where your data frame can load into memory fine. Let's say I have a 40 gig CSV file. I launch a machine with 100 gigs of RAM. I can load that file just fine. But then whenever I try to do any sort of operations with it, you're just kind of stuck waiting. And this is because pandas was written in a single core paradigm, right? Everything only executes within one processor core. So you can load your data and you can do stuff, but now you're kind of stuck waiting for things, right? So, you can try to hack together some multi-threading, multi-processing type stuff, or even certain libraries kind of in this, I'd say like traditional toolkit do support multi-threading. So like there's within the random forest model in scikit-learn, you can specify this njobs parameter to train multiple trees all in parallel. So this is great, right? This is kind of what you want. You want to be saturating all of your resources. So, you've got your big data set in memory. Now you're using all your cores, but you're still kind of running into this problem of it's taking a long time. You can use all your cores on your machine, but if you're processing a big data set, you might still be hitting the bounds of that, and you might still kind of need more power. And then that's really where Dask comes in. And we're going to talk a little bit more about that. So this is where also when we're thinking about this concept of scaling, right? So I showed you a few different scenarios. One of them was that your data set just plain couldn't fit into memory, right? So you're stuck there. You need more memory. But then there's also scenarios where maybe your data set does fit into memory, but you're training a really complex model, or you are doing a hyperparameter search or anything that's going to require a lot of computations. It'll work, but it's just going to be really slow. And you don't really want to have to wait a few hours or overnight or over several days for experiments to finish, because that becomes now your iteration cycle. If you iterate every 3 days, it's going to take a long time for you to get to like a good model, versus if you can iterate much more quickly in the same way that you would if models would train kind of faster, your data would process, more or less instantly. So those are kind of a few different cases of when like you want to scale machine learning. Basically, you want to add more machines, so that way you can either process more data or you can just do more computations all at the same time. In this workshop, we're focusing on this memory bound case, and when you have data sets that are just kind of too big to fit within a single machine. And when it comes to the machine learning, it's not only training your model, right? Like that's one thing, but you also have to process your data. You have to extract features, you have to clean it up, you have to do all kinds of other things. And that, typically might be some sort of like data frame operations or just arbitrary Python code to pull whatever data that you have. You format it into a nice clean tabular format, and you have your X and Y, and then you now can pass that over to a machine learning model that's going to do something. So those are the two things that we're really focusing on, is this kind of large data processing, because you need to do that before you get to the machine learning, and then the actual like model training with these large data sets. We'll have a follow-up workshop that covers some more of these compute bounds or diving into some specific models and deeper topics. So this is where Dask comes in. And Dask, if you haven't heard of it, it seems like some people here on the workshop have experience already with Dask. But if you're unfamiliar with it, it's a Python native parallel computing library. And a lot of those words are really important, right? Parallel computing, first of all, is this idea of being able to now chain multiple computers together, so that way we can process larger data sets that wouldn't fit on one single one of those machines. So you got to get the hardware somehow, and then you have to have all the machines talk to each other. And as a data scientist, you don't really want to have to be thinking about like cluster computing and like writing custom code to think about which piece of data is on which machine and then collecting up the results. What Dask does is allow you to use some high-level interfaces that will automatically kind of like spread the code and computations across your cluster. So it has APIs for data frames, arrays, machine learning, and a couple other things. But what's really cool is that you can actually drop down, and it's built on this foundation of a low-level task library. So there's some code here on the right, and we're going to go into this in the workshop, but the idea is that you can put together these building blocks of different functions, and then Dask will handle distributing that across the cluster. So you're still kind of writing the Python code. You're thinking about your business logic instead of kind of like this orchestration. And we'll kind of cover this low level and then the high level. We're going to spend most of our time on the high level part, but the kind of low level task library is really, really powerful when you have kind of like complex computations that you would need to run. And so part of this workshop is that we want to like show you Dask and we want to show you how to use it, but we also want to help guide you in your journey of machine learning and data processing for like, what tools am I supposed to use, right? These days, pandas is tried and true. We hear a lot about kind of like Dask and cluster computing, but sometimes it's like, okay, I just need to do a thing. I just need to get my work done. And it's not happening this way. What tool do I need to use? And the consideration at the top here is pretty important, is that because of the flexibility of Dask being like really tightly integrated with the PyData ecosystem, it allows you to only scale when you need it. So you can start off with a pandas data frame, do your processing, but you have some complex function that needs to run. It takes a long time for each record. You can now do that with Dask. And so there's like a lot of different places that you can put this in and out. And here's a whole list of different considerations for different parts, I would say, of like the data science or machine learning pipeline, where you might be fine using pandas, but then where you might want to kind of switch over to using Dask. But there's a few of these scenarios. And again, in this particular workshop, we're going to be covering when your data doesn't really fit in pandas anymore. So it's like 20, 30, 40, 50 gigs or more. you're going to have a bad time with pandas just because it's going to be slow on a single core. And then when you get to the model training point, if your data is small and it trains pretty quickly, you're fine just using your single node with scikit-learn. But again, if you have this large data set that wouldn't even fit into pandas, then you're really not going to be able to train with it in scikit-learn, right? And so that's when you're going to use Dask for the model training. And then those are other considerations that we'll cover in future workshops. Okay, so we've talked about like the idea of cluster computing. We've talked about the idea of like scaling out your machine learning. And we talked about Dask, which is this great open source tool that will kind of handle all the software for you. You can write stuff in, like, your code looks like pandas or NumPy, but it's actually executing on a cluster. The challenge now with that is, like, how do I actually run it on a cluster? Like, how do I get 10 machines and how do I get them to all talk to each other? The great thing about Dask is that it has a lot of options for deployment. So, but it's still kind of difficult, right? You have to like either spin up a cloud thing, and you have to be like a DevOps expert to like connect to all the networking and make sure all your nodes are running, or you have to know Kubernetes or Hadoop or anything like that. And so these are all different options that you could use with Dask. But the reason Saturn Cloud exists is to make this really easy and accessible for kind of any data scientist, whether you're like a lone data scientist or somebody on a team at a company, to just spin up machines, get working, accelerate your Python code. And so that's really what we're covering today. So there's two offerings of Saturn Cloud. Most people here are going to be using the hosted platform, which is a platform where we kind of have a Saturn instance hosted, and you can kind of sign up, just put in your email address, and then put in a credit card for the billing, and then you're kind of off to the races and you're up and running. We also do have enterprise installations where we'll install Saturn Cloud into your specific AWS account. So that's really important for data security, or if you have a large team, you can use that enterprise platform. But this hosted platform is really good. Again, if you're an individual, if you're learning, this workshop is a perfect place for that. And we've given all of the people who signed up as participants, we've given you all some credit, so that way you're not being charged for any of the work that's happening in the workshop. And you'll even have some credits left over to play around yourself afterwards. So with that, I think we kind of want to just dive into the code and the workshop. Does anybody have any questions so far, just before we get into the code? Anything of just what is Dask, what is Saturn, like what are we going to cover in the workshop? You can kind of open that up. If you want to use Slack or the Zoom chat, or just kind of talk, you can totally do that. Going once. Okay, great. Well, let's go ahead and jump in. So for those of you who signed up as participants, you all should have received an email with your hosted account creation, or if you already had an account, you can go ahead and log in, because you might be familiar with doing that. These two here are some links just for a future reference for you to go in. And actually, let me give you a link to the slides right now in the Slack channel, just in case anybody needs these links. So there's a PDF to the slides. All of this code is available on GitHub. So I'll go ahead and just like paste this GitHub in as well. In case you're somebody who signed up as a observer and you want to kind of try this yourself later, you can go to this GitHub page. It has all the instructions for setting up your project, cloning the code, and then all the notebooks are here. But for now, we're just going to go ahead and jump into Saturn. So I want to make sure that everybody can log into their Saturn. Everybody who's participating can actually log into their Saturn account. And can you see this screen? Go ahead and give me a thumbs up on the Zoom if you can see this projects page. If you have any trouble, again, feel free to let us know. I saw a couple of thumbs up. Is everybody accessing the project page okay? Okay, awesome. Okay, so what I'm gonna do is one of the notebooks in the GitHub repos has like an overview of Saturn in case people who are kind of looking at this later. But what I want to do is just give a quick overview into the product, just so anybody who's not familiar with it kind of knows what we're working with. So everything in Saturn Cloud generally starts from a project. So this is just kind of a way for you to kind of group up any sort of work that you might be doing, but it's really housing different hardware resources. So I have a few more projects than you might have, but we're working here now with this workshop Dask ML big data project. So if you go ahead and click through into that, you'll see, let me zoom out, just one tab, okay, here. So you'll see a project here. And so there's several different components to a specific project, but your two main kind of hardware resources, if you want to think about it like that, are a Jupyter server and then your Dask cluster. So the Jupyter server is a machine, this one single machine that's running your Jupyter lab, and you can do any sort of work that you might want to on there. So if you just need a single computer, again, if your data is small enough just to fit in pandas or anything like that, you can just run up this Jupyter server, and it's optional to kind of attach a Dask cluster. But in this case, we're going to be scaling our work across a cluster. So we have a Dask cluster. If you're a participant, your resources should already be running. We have this Dask cluster here. We've set up 5 nodes on the cluster for this particular workshop, but you can kind of go ahead and edit your cluster and kind of choose any number of different resources. So let me just show you that real fast. I already have mine live, so I don't want to change that, but I can show you what it looks like to kind of edit any of these resources. So we see here that there's a lot of different choices for what instance or machine that you might want. I think we're working with this X large that has 30 gigs of RAM, but you can get up to 500 gigs of RAM or multiple GPUs on your machine, and then it's the same choices for your Dask cluster. So it's really flexible with what you want to do there. Also want to talk about the concept of this image. So an image here, behind the scenes, it's a Docker image that has all of the Python libraries that you might need installed. We have several images that we've kind of pre-packaged into the hosted product already. So this latest kind of Saturn image is going to have all the libraries that we're going to need, Dask, scikit-learn, pandas. So you don't have to worry about that. If you wanted to add like one package to your particular machine, you could actually go down here to the SCART script. And in this case, I did pip install pandas. It's already there, but let's say you wanted like matplotlib. What happens is when your machine spins up, it'll pull that image. So that way you have all those packages that are already built into that Docker image. But if you needed one or two things on top of that, you can add it to your start script right here. If you needed a lot of custom stuff, you might want to think about building a new image. And if anybody wants to do that, you can kind of talk to us later. That's kind of outside of the scope of the workshop for now. But let me go back to the project that we're working with, this Dask ML big data project. So one thing I want to note is that you'll see a few lines in your start script here. This is something that we've added because XGBoost actually just had its latest release. We wanted to make sure that everybody is up to date on the latest XGBoost package. We're going to use that a little bit later on in the workshop. So this is one of those things where it's like, oh, okay, we needed to make a small tweak to a couple of the packages, so we put it in the start script. In the future, we'll have the newer version in the image, so then this start script won't be necessary. So for now, you can pretty much just ignore it, and then in the future, everything will be fine. Cool. I think I covered everything as far as what we need from Saturn. The rest of our time in the workshop, we're going to spend inside of Jupyter Lab. So go ahead and open up the Jupyter Lab for this particular project if you're following along, and it should look something like this. You should be within this, you should see this project folder here, and then you can double click into this, the workshop folder, and then you should see a handful of notebooks here. And let me zoom in just a bit. Okay. So what I want everybody to do is go ahead and open up this O1 start notebook. Pretty much all of the stuff, all of this text here, I already went through it. I introduced to kind of all the different concepts of Saturn, but go ahead and scroll down and just work through this notebook. There's a couple different cells here. The main thing is that I want to make sure that these cells like run and execute properly for you. I'll go into specifics of like the details of like what we're actually doing later on, but I want to make sure that we're all starting off with at the same place. All of our hardware is up and running. So go ahead and run through these few cells and then get all the way back, all the way down here to Kip. If you're a Napoleon Dynamite fan, you'll recognize him. Go ahead and work through that and then give me a thumbs up when you're done. I'll put like 2 minutes on the timer here so that way everybody can kind of get situated. Okay, awesome. Great. Well, let's go ahead and move forward. So the second notebook here is basically just trying to illustrate what a particular workload might look like on like a single machine if you were doing it with just your typical pandas, scikit-learn type stuff. I'm not going to run through this now, and I'm not going to really require everybody to run through this because the kind of assumption is that we've kind of already done something similar, but I want to just give some groundwork and give some background like to the data set and the machine learning problem we're doing, so that way later on we can focus just on like the Dask and scaling pieces. So actually, if you want to follow along, there's this folder that says executed, and it actually has that same notebook except with all of the cells executed, so you can kind of see some of the outputs. But I'm going to just kind of breeze through that real fast now, again, just to give a background on what we're doing, and then we'll jump into actually the meat of the content. Okay, so actually I'm going to open up a terminal window because I want to show you like the resource utilization that we've got. So I'm going to put this over here to the side, close this for now. And HTOP will just show you like your different processors and the memory usage on those. So I'll just kind of run through some of these cells and then show you what's going on. So for this particular workshop, we're using some publicly available taxi data from New York City. Each record in the data set covers one individual taxi ride. It's like the pickup location, drop off, pickup time, drop off time, and things like that. So the machine learning problem we're going to go through is trying to predict like how much a particular rider is going to tip the driver. So we have some data here, and you can see we have like the tip amount and the fare amount. So basically, we're trying to calculate the percentage of this. It's like, is somebody a good tipper, right? Are they tipping 10%, 15, 20%? So we're doing some regression to kind of predict that, as our little toy problem. So all this data is publicly available on S3. So if we were to load up a data set, in this case, there's data from like 10 years. We're going to focus on, for our like large data set, we're going to use data from all of 2019. But the data from all of 2019 is kind of already too big to load into pandas. So in this case, we're just going to be loading 1 month of data from January 2019. So you see that takes a few seconds to load, but then we can preview our data and do our pandas stuff, right? So it looks like we've got like 7 million rows here, and it's about 1.5 GB in memory. And you can see now that I have like 3 gigs being used on my machine. So as far as some exploratory analysis that you might do, I'm just calling describe from pandas, and that's giving me some information about all the columns. I can see that somehow somebody paid $600,000 for a taxi ride. That's probably some messy data or a really long ride. And we can kind of look and explore our features. Of course, you might do a lot more processing in your case. So to do the machine learning, we'll need to do a bit of feature engineering, right? So this, again, the point of this workshop is mostly just show you how to scale this stuff. So I'm not saying these are the best features. The models aren't going to be great, but this is just to kind of illustrate what we're doing. So in this case, we'll just create a function that does our data processing. So we'll filter out some data, because if the fare amount is less than 0, we're going to have a divide by 0 error for the percentages. And then we'll just calculate. Right now, we're just extracting some features out of the timestamp. So based on like when somebody was picked up, we can maybe, and like the number of passengers that are in there, we can maybe determine like what they might tip. Maybe someone in rush hour is going to tip a higher percentage than, at like 9 p.m. or something like that. So now this is the data set that we're working with. We have a handful of features, and then we have our class label. Not class because it's regression, but this is what we're predicting right here. So now we're jumping into some scikit-learn territory. We'll do a train test split, so that way we can train our data on the training set, and we'll use a 30% holdout set for our test set. And then we'll train a model. So in this case, I'm doing a linear regression just with an elastic net and setting up a pipeline, because if we're doing a linear model, we want to make sure that all the features are scaled. So we'll do some scaling, and then we'll train the elastic net here, and then we can kind of fit on this pipeline. So I'm gonna run this and show you kind of the resources kind of running up. So you see how like we're kind of using, there's like a couple cores running right now, but like it didn't really quite use all of the resources on my machine, right? And that's where we want to be able to like parallelize the stuff really well. So now you can kind of get your predictions and then get your mean squared error. So it's like, yeah, our mean squared error is 5, and so when you're getting an MSE of 5 and you're trying to predict a percentage or a fraction, that's obviously a really terrible model, but that's not the point of kind of what we're trying to do today. So the idea is, right, now we've gotten to the point where we're like, great, we trained a model, we processed some data. Well, let's do it with more data, right? And so if we want to do that with pandas, we would have to like write a for loop, because there's like one CSV file for each month in the year in this particular data set. So in this case, I just used S3FS to kind of like get the sizes of each of the files. And so each file itself is like 600 megabytes. And then there's 12 of them, right? So you could write some for loop and say, okay, for each file, I'm going to grab it and I'm going to keep a list of them, and then I'm going to concatenate them together inside of pandas, right? So this is what that workload might look like. I created some function that'll like read a CSV file, and then I have a for loop that's going to read that one and then collect a list of all of those data frames and then concatenate them together here into one big pandas data frame. But if you're following along, don't run this cell, because it is going to explode. Like, this is where we're going to get to that dreaded memory error. Yes, you could launch a bigger machine, right? And then it would fit into pandas, but it's still going to be slow doing things because it'll be single core. So this is our like failure scenario now, where we're going to try to bump up and scale up higher. And so like the next thing we would want to do is just train a model, right? But we couldn't even load the data in the first place. So how are we going to be able to train a model, right? So that's where Dask comes in. Any questions so far? We're actually going to get into hands-on stuff right now, I promise. Okay, great. So what we'll do now is I'll give you like a good intro to Dask, some of the key concepts that you might want to think about when you're working with Dask, and some of the essentials, and then we'll take a break, and then after that we'll kind of really dive into this like machine learning pipeline. So I already talked a little bit about what Dask is, why you might want to kind of parallelize some of your code, but we're just going to jump in and then get working. So this might look familiar from the first notebook, but we want to start up our Dask clusters. So from Saturn, I can see that I have a Dask cluster running right here, right? But if I want my Jupyter notebook now to be attached to this Dask cluster, there's a couple lines of code we need to add here. So if you're familiar with Dask, you're used to this kind of paradigm. Basically, you always have a client for Dask. That's Dask's entry point into whatever cluster you're running. But then you would swap in some different kind of cluster class based on like what specific cluster you're running. So if you're running on Yarn or Kubernetes or whatever. So in this case, we're running it inside of Saturn. So we have this Dask Saturn package that provides a Saturn cluster that you can pass into this Dask client object. So in this case, we have some parameters here that match. This is basically specifying like the size of the machine. So my worker size is an X large. This is a machine that has 30 gigs of RAM, and I want 5 workers. If your cluster was off, like if I were to go in here and click this stop button from Saturn, and then I were to run this cell, this would actually trigger the cluster to start up. So you'd wait a couple minutes, and then your cluster would kind of be up and running. But if your cluster is already running, you can run this cell, and then you should be able to get your client back pretty quickly. And so you should see something where it says cluster is ready, and then you might see a couple more outputs as well. But as long as you see this cluster is ready thing, you know that you're good to go. So, if you're specifying your cluster from within the code, you might be wondering like, what does this medium mean, or what does this X large mean? We have a function within this Dask Saturn package that'll also tell you that. So you can run this, and then it'll tell you, this is very similar to that drop down that you saw within the UI, but now I can see, okay, this key means I'm getting 4 cores and 30 gigs of RAM, and then you can kind of pass in all of those like different values. Okay, so I mentioned this client, this client object, and this is really important because this is where we get into Dask. This is where we can now start to hook up some of our other Python code into Dask. And this is a client. So if you were to just preview the client object, it gives you some information about your cluster. And so you'll have some data here that'll say, okay, I have 5 workers, 20 cores, and RAM. But the most important part from the notebook's perspective, it gives you this link to this dashboard. And this dashboard is a really great place to monitor your Dask cluster and all of the things that are happening within it. So I would recommend, if you're following along, if you have a pretty big monitor, try to rearrange your windows so you can have the Jupyter Lab window up and your Dask window up, and you can view them at the same time, and then also have Zoom up so you can see me. So If you need to swap back and forth between JupyterLab and Dask, that's okay. I'll do that now, but I really find it really useful to have my code here and then my dashboard somewhere else so I can see it light up. You're probably just going to be watching this main page right now. It's not doing anything because we're not doing anything with Dask, but you might find it helpful to go over to the workers here too, and you can see some numbers about like what's happening. This is each of our 5 different machines, and then other things that are happening here. You can also get to the dashboard from within Saturn right here as well. Okay, so one thing is that Dask clusters are, you can scale Dask clusters live. So in this case, I asked for 5 workers. So what happens behind the scenes in Saturn is we spin up the cluster. So this is just like kind of like the manager of the cluster, and then your workers will come up live. So your cluster object, if you're starting it off fresh, it'll be already, but then you might not quite have all your workers because nodes have to spin up, that Docker images have to be pulled and such. So in this case, I always like to make sure to do this wait for workers. So because that way I know that I have exactly 5 workers ready for me to go. So if I wanted to scale, I don't recommend you do this now because we want a 5-node cluster. But if you wanted to, you could do something like, if you wanted 10 more nodes, you can do cluster.scale, and then I could do cluster.wait for workers like this, and then wait for 10. Or I could say I don't want to wait. I could let my processing keep happening, and then as nodes would come up, they would get incorporated into the task graph. So Dask is smart like that. It'll be able to work with what you've got. Of course, more workers means it's faster. So I always like to wait for it just because I like to time my cells and know exactly how long things are running. Okay, give me a thumbs up if you're good to go from here. This cell is showing you this ready to go. Okay, awesome. Great. So now we're gonna, so that's always, this is kind of like some boilerplate stuff that you're always gonna do at the beginning of your notebook that's using Dask. Okay, now we're gonna get into some of the Dask concepts, and this is really important, this concept of lazy evaluation with Dask. So if you've never really worked with any sort of like cluster or parallel computing tools before, this might be a concept that's new to you. So I want to make sure that we kind of like hone in on this and make sure everybody's on the same page with it. So I won't read all these words, but basically the concept of lazy evaluation is you're calling functions that are supposed to do things, but Dask doesn't quite evaluate them right away. What it does is it builds up a task graph of things that you want to do, and then you can call specific functions to say, give me the answer. And this is important because if you're loading like a bunch of data that doesn't fit into memory all at once, and you're doing some processing and doing some other things, Dask can optimize what you're doing, but it has to wait and know all the things that you might want to do first before it actually executes. So that's this concept of lazy evaluation. And it's illustrated really well with this kind of low-level building block, which is called Dask delayed. So pretty much a lot of the stuff that's built in Dask is built on top of this concept of delaying functions. And so the high-level dataframe API, the high-level arrays, even other libraries that built on top of Dask, at the low level, they're probably using an interface like this. So we'll start off just first of all, which is like a regular function. So I made this random function called multiply, and you can call this with 2 different numbers. It'll multiply those 2 numbers, right? So that's just like a normal function. That is something that executes immediately because this is a regular Python function. So now we're going to go ahead and import Dask and use this Dask delayed decorator. And what this does is you see this function is exactly the same code as my other function. But what this decorator is telling Python is that this is going to be wrapped in a call to Dask delayed. And so what happens now, if I run this cell, you'll see that I don't get my answer. You know, I know by reading this that my answer should be 6, but I don't get my answer yet because nothing actually happened yet. Because you're telling Dask, delay this, run this, evaluate this in a lazy manner. And so if you wanted to actually get the answer, you would call compute on this output. So you could save this result to an object. In this case, I'm just calling the function and calling compute right away. And in this case, it runs really fast because it's a pretty small function. But if you run this and switch over to your Dask dashboard, you should see something kind of running up. It's really fast, so I'm only showing you one window, so I'm not going to be able to like see it, but you can see that some task executed right here. So for one particular function that's multiplying numbers, it's not all that exciting. But the really powerful part is when you can chain together multiple delay functions. So in this case, this multiply Dask is returning a delayed. It's not actually giving me my answer. I'm calling it again with some different arguments. And then I'm even doing some operations with the results of those two calls. So Dask somehow knows that there's numbers that are going to be passing through between all of these functions, and it's going to result in some other number. But again, if I try to preview this last object, it's just this delayed object, and I haven't gotten my answer yet. So I want you to try in this exercise right here is actually based on what I've showed you before, try to go ahead and get the result of this of Z here, and give me a thumbs up if you're done. If you want to cheat, you can click on this ellipsis and get it, but go ahead and give it a shot, because I think you should be able to do that. I'm not going to put a timer for this because it should be quick. I'll give everybody a few seconds to try it out. Okay, awesome. Great. Well, if everybody got it, you can see the answer is kind of right up here, but we can click this, and then if you call compute, you would see your answer. So now when I call compute, Dask is like, oh, okay, you called this multiply function here, you called it again, and then you multiplied those results to each other. It'll go back through, execute all of that stuff. And this is powerful because if I had this function like loading some files from somewhere, and then a lot of these tasks could happen in parallel, Dask would actually do that. So you can even go over into this graph here, and you should be able to see the last task. Well, again, this is going to happen really fast, so you might not see it. We'll see that. We'll go and look at that graph later on. But now we've kind of got our answer. So compute is really powerful compute is really important because you need it to actually like trigger Dask to actually do things. There's another concept of persist, which I think I'm going to kind of discuss a little bit more in one of the future notebooks. But persist also triggers your graph to compute. And so the only difference between this persist function and compute is where the result gets sent to. So in this example, when I call z.compute, it's giving me my answer right back inside of my Jupyter Lab, right inside my session. The problem is if this z object was too big to fit into memory of my Jupyter Lab machine, and I called compute, we would be at the same problem that we started off with. It would blow up. So what persist does is it's almost like checkpointing. It'll execute your entire graph of tasks that you've executed, that you've specified up until now, but it's not going to pull the results into Jupyter Lab. It's going to store the results across your cluster. So it'll store the individual results across all the different nodes in your cluster. So this is really helpful, like if you're loading files from a database or from CSV files, and then you're doing a bunch of processing, you can call persist, which will trigger Dask to do all that processing across your cluster. And then you can go ahead and do more things like training a model or doing even more pre-processing if you needed to. So that's kind of the differences here between persist and compute. So that's most of the intro for like the Dask basics. What we covered here was how to connect to your cluster, lazy evaluation, and then a quick differences here between persist and compute. We're going to head into a break, but before we do, does anybody have any specific questions about what we've covered so far? Feel free to ask in the chat. I know there's some chatter in the chat happening right now. Keep that up, or you can unmute now and ask a question. Okay, cool. So what we're going to do now is we'll do a 10-minute break because I know I threw a lot of information at you. I threw some slides at you. This will give you an opportunity just to kind of walk around, get a drink, or if you want to kind of catch up a little bit, maybe you were following along and didn't really run all the code. This will give you some time to go through all of the notebooks that we've gotten to now. But for now, we'll do a 10-minute break and we'll come back at 2 p.m. Eastern. So I'll set a timer for that. Great. Okay, so this is where we're going to really start to dive into some of the work, and we're going to put together the concepts that we just talked about, and we're going to do that same workload we talked about on the single node, except now with a large data set. So this part, if you want to have your hands on the keyboard, I'm going to have a lot of exercises for you to come here in and fill in. So make sure you're following along. So the first thing that we're going to want to do is we're in a new notebook now. So in each of your notebook, or really each of your like sessions that you're working with Python, you're going to want to connect back up to your cluster. So we're going to run those same commands. So go ahead and see if you can like find the commands and the right arguments to fill in here from the previous notebook. Again, you can cheat if you want to click this ellipsis. Oops. Oh, I just showed it to you. If you want to click this button here. And so like I was saying, is you're going to need to kind of run this inside of each session. It's not going to like create a new cluster for you in Saturn. It's going to connect to the one that's already existing within your project. Or if the cluster happened to be off for any reason, if you turn it off or if it is off, this will also spin it up. So it might take a little bit longer for you to run this cell. And then we'll run this wait for workers to make sure that like all your workers up. Again, give me a thumbs up when your cluster's up and connected and you can see your client there. Great. Okay, awesome. So this is it. It's exactly the same code that I had showed you in the previous notebook. And then we also want to make sure that we wait for our workers here and then we spit out our client. This is where you're really going to want to watch this Dask dashboard. It's the same link as it was before. So if you already had it up on a different tab, you're good to go there. Okay, so here we go. So what I'm going to show you is using, so the first part we did right with pandas and then we did stuff with scikit-learn. So the analogy here, instead of pandas, we're going to use the Dask dataframe module. And so that's what's happening right here. And so the pattern is to just give it an alias of DD. So we're going to import Dask dataframe as DD. And then we'll use this wait command later. I'll show you kind of what that does. But in this case, this is essentially now, instead of PD for pandas, it's DD for Dask dataframe. And the API is going to look really similar. So go ahead and run that. And the one difference you'll notice with the Dask dataframe kind of like read CSV function, which mirrors the same kind of stuff that you would do in the pandas function, is it actually accepts a list of files, or it'll accept like this glob syntax, which is like you can say, give me this file path, except put an asterisk here. So it'll take anything after 2019 dash. So in this case, we're gonna get all of the files of 2019, 01, 2, 3, blah, 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 all the way up for each month. So in this case, to this read CSV, we're going to pass that list. I could also directly grab this string and put it into the DD read CSV because it accepts like this glob syntax. I was just doing this in a different object here just to show you like what the individual files actually are. So this read CSV, a lot of the parameters are similar to what you would encounter in pandas. There's a couple things here that are Dask specific. So if you notice here, this parse dates is exactly the same as pandas. When I went to this 02, we can scroll back up here and find it. So I'm just telling it which columns need to be parsed as dates. There's a couple Dask specific things here. In this case, because we're reading directly from S3 and we don't have any S3 credentials, I mean, you might if you set that up on your hosted account, but in this case, we're assuming we don't have S3 credentials, but we just need to make sure that we're passing through an anonymous connection. So that tells Amazon that I'm not trying to authenticate, I'm just reading this because it's a public bucket. And so that's that. And then assume missing true here is this is because when you load something with pandas, it's going to go ahead and process each line and read it into memory. When we're calling this read CSV function, remember this concept of lazy evaluation. Dask isn't actually loading all of these CSV files yet, right? So look, watch, I can run this and it's going to run instantly. That's 12, this is like 6, 7, 8 gigs of data. Dask didn't actually like load all of this. So what Dask is doing is it's keeping pointers essentially to all these files and it's trying to figure out metadata and things like that. So when we're saying assume missing equals true, this is just saying treat any integer types as float types, because with pandas, you can't have any missing values inside of an integer type column. So this is telling Dask anything that's numeric, just treat it as a float because we're not sure if we're going to encounter missing data. That's just, again, one of these consequences of doing this kind of lazy evaluation, because if Dask thought, in one file it was integers, but then it encounters another file where it's nulls, it's going to have some data type problems. And this is also illustrating the fact that Dask is really Dask data frame is an extension of pandas. So things that happen in pandas and some problems that you might run into in pandas, a lot of them are going to translate to Dask data frames because it's using pandas under the hood, as we'll see. So we've got that. We've got this taxi object now, right? So when I preview this taxi object, it's different than what I would get from a pandas data frame. In this case, Dask knows what all the columns are, but now it's telling me that it has 127 partitions. So Dask, of these 12 different CSV files, it's figured out 127 different chunks that it's going to do and use for processing the data. So when you go to actually execute things, there's actually going to be 127 processes happening in parallel. And Dask kind of figures that out. You can alter that and change that, but for now you won't really need to do that. Dask is pretty smart. Okay, so now here's another exercise. I want you to go down here and try to get the number of rows in the taxi data frame. Again, the Dask dataframe API matches pandas in a lot of places. So try it in the same way as if it was a pandas data frame and see if you can get the answer. Okay, so you might have tried a couple different things, right? Because within pandas, there's a couple different ways to do that. You might have tried to do taxi.shape. And that's not quite the result of what you're expecting, right? This looks familiar from the last notebook, right? This is this concept of lazy evaluation. Dask hasn't actually loaded all this data, so it actually doesn't know how many rows are inside the data frame. It does happen to know how many columns are here because that's one of the things that it was doing as kind of preprocessing to make sure that, that it was able to load all the data into a data frame, but it hasn't quite actually done it. So what you could do is, from our last exercise, is called compute on this, right? So in this case, you would have to do like 0 to get the first element of the tuple, and then you could call compute. And I think I actually do this later on. Yeah, so you can do this right here. So you could call that, or you could just do like len taxi. So in this case, when you call this len function, it's a special case where Dask knows, oh, the user wants me to actually trigger the computation, and it wants me to actually like do something. So go ahead and run one of those two things. There's the answer here, or run this shape compute. It's doing the same exact processing under the hood. Only run one of them. You don't have to run both, but you'll notice that it's actually going to take a few seconds. And if you go over to this dashboard, you're going to see it actually processing stuff. Oops, mine just finished. Let me kick this off one more time. You go over to the dashboard and you can actually see it doing things. And this matches, so you can see here, okay, I have 127 different tasks, which is first it's going to read the CSV, and then it's going to compute the length. And what's cool is that all of these are actually happening in parallel. So each of these bars, like this horizontal section, corresponds to one of the cores in your machine. So if you looked at our cluster, we have 5 nodes that have 4 cores each, so we have 20 cores in the whole thing. So each of these lines represents a core doing work. And when this graph is full, that's a good thing, because that means all of our processes are happening and doing things all in parallel. So this length thing, computing the number of rows, is something that you can do independently, right? You have 127 chunks, you get the row count of each chunk, and then you just give back the sum, which is really small and easy to compute. So you can see that actually in the graph as well. So I'm going to run this one more time, and the graph is going to show you exactly what's happening. So here it's loading CSVs, it's computing the length, and then it's going to give me back the answer. But it's really cool and fun to watch like all the different things happening and execute. Okay, so we're going to let that finish. And then the next thing that we want to do is, I think I showed this to you on the last notebook, but we want to get like the memory footprint of what we're actually loading, because I want to just make sure that my cluster is good, make sure that I have enough memory in my cluster to do any of the future processing that I might need. So right here, this is how you would do it in pandas. It's the same exact code to compute the memory usage. But then again, notice I ran that, it returned instantly, and it didn't give me my answer because this is another one of those kind of lazy evaluation things. So you guessed it, there's another exercise. Get the answer of this taxi bytes result. Give me a thumbs up when you're done. Okay, cool. So hopefully you got that answer right, but I'm just going to go ahead and execute that now. This might take a little bit longer, and you see now I have a different task graph that's showing up because it's doing some different work. So it still has to read each CSV file into chunks, but now it's computing the size of them all independently, and then it's kind of combining some things here and there and like figuring out, and at the end, again, it's going to give me my answer. But if you've noticed, it's repeating this CSV loading. So because of this lazy evaluation, Dask will read the CSV, give you the answer, and then next time you want to do something, it's actually going to go back and try to read the CSVs again. And so that's not always the best, right? That's really helpful if like your entire data set does not even fit into memory on your cluster. So it's like if this data set was like 50 terabytes and you wanted to process it, you could still do that with Dask because it would load in certain chunks whenever it needed it, and then it would kick it back out of memory. So that's really helpful if your data set is just like really, really humongous. So it might take a long time to process, but it'll actually work. But in this case, we'll we want some of that CSV loading to kind of happen once, and then we want to be able to like execute all of our stuff faster later, right? So I don't want to be rereading CSV files all the time. That's where persist comes in. So you don't want to call compute on taxi. If you run this taxi compute, what this is going to do is going to try to load all that entire giant data frame and give it back to you as a pandas data frame, because this taxi object is a Dask data frame object. So compute will give you back everything. That's what you don't want. Compute's fine when it's a single number like this command, but it's not helpful when it's like a really, really giant object. That's where persist comes in. So you can go ahead and kick off this persist command. And what this does is it'll trigger the reading of the CSV files, but it's going to store those results across the cluster now. And so you can go back to your status and you can see things happening. And now all it's doing is executing read CSV. And it's doing this in parallel, but then it's going to hold the results in memory. So if you look at this bytes stored up here, you can see this is slowly creeping up as it's loading up more data. And okay, so now it's done. So now I'm going to have this persistent 18 gigs of RAM sitting in my cluster all the time because I asked Dask to persist these results. So this 18 gigs, you wouldn't want to have pulled that into pandas because it might have blown up, right? And so now this is really helpful, again, looking at this dashboard, because you want to make sure that I still have some room to do things. Because just like pandas, if you load in a data frame, you probably want like anywhere from 3 to 10 times the amount of memory of your data frame to be able to do processing, because it's gonna consume RAM as it needs to do things, group bys and such. So similar idea with the Dask clusters. You don't really want your persisted data frame to go any farther than maybe like 30, 40%, because otherwise you might run out of RAM when you're doing things. But if you need more RAM, it's really easy. You just run that scale command, scales up, and then within Saturn, you're just paying hourly for kind of your usage. You can scale it up and then scale it back down when you're done. Okay, so if you notice, actually, I'm going to run this persist again, but this also returns immediately. But things are still executing in the background. Actually, it's already done because I did it. So in this case, I always like to pair this wait command with persist, because Dask, what it does is it'll persist this, but it'll let you keep going, because it's like, oh, okay, I'm going to work on loading your data frame, but I'm going to let you keep coding and doing some of your other things and then chaining up more processes. But I like to, especially when I'm doing machine learning and other things, I like to time each individual processing step. So in this case, if I were to run persist, I can run this wait command, which will actually block my session until the object is fully persisted. So in this case, if you ran these immediately, then this wait command will essentially tell you like how long it took to execute this CSV reading. And then now what's really cool is we can run the same exact memory usage command, but then it's going to return way faster, because that took 2 seconds. Whereas before, it took 30 seconds, because the last time the data frame was not persisted, I had to go back, read all the CSV files, and then compute the size. In this case now, the data frame is persisted, it's sitting in memory. Dask doesn't have to go that far to get the data. It's already in memory on the clusters, and it'll just execute things there, give you back the answer. Everybody good on that? On that concept? Hopefully that's just starting to now piece together some of what we had talked about from a high level, and then like really making it so you can do real things. Okay, awesome. So this is a quick aside, but I think it's really important, because I talked about the fact that how there's these high level interfaces for doing things with Dask, like the data frames, there's arrays, and there's machine learning, like we're gonna look at in the next notebook. But a lot of the times you might be working with data that's not really super clean, that doesn't really fit into the paradigm of a data frame. And this is a really common pattern. I do this a lot. We see customers doing this a lot, where you have some data in some database somewhere where there's not like a native connection, or these weird flat files or JSON files, or just like all kinds of different weird formats. And if one of the kind of read underscore functions in the Dask data frame library doesn't work for you, you're going to want to drop down to doing this using this delayed interface. And so what's really cool is that this delayed will also work with the data frames. So you're going to see here in this quick example is that I'm going to specify like arbitrary functions that can load or create data. And each of that output of that individual function is giving me back a pandas data frame. But then if there's a big collection of pandas data frames, I can tell Dask, hey, orchestrate all of these individual data frames as one individual Dask data frame. And then now you can work with one data frame instead of a whole bunch of different ones. So I know that might be a little bit of fuzzy, but hopefully running through this example will actually explain that for you. So what I'm going to do actually is I'm not going to walk through all this live. I want you to kind of go in here, read it, run these cells, go through this all the way up through the exercise, actually all the way through down to right before the exploratory analysis section. So I want you to go through this entire messy data, Dask delayed, read through the text there, run the cells, try the exercise, and then you can go ahead and pause once you get to exploratory analysis. I'm going to set a timer. I'm going to let you read through that stuff, and then I'll come back and explain it later. Okay, hopefully you've gotten through to that section. We have a few more seconds, but I'm going to go ahead and get started here. So hopefully that section has kind of like showed you a bit of how you might work together with Dask delayed into like data frames. So I'm going to go ahead and run this. So essentially what this is I have some function that will create a data frame, or this would be replaced with anything that actually would do your data frame loading. And then I can collect a list of all of these things. Again, they don't execute right away, but then I can do this Dask data frame from delayed function that'll know and understand that this is a list of things that eventually become pandas data frames, but I want to convert that into a Dask data frame. And this is the result. So you wouldn't normally call compute, like I said, but now this is kind of like what would have been output in this toy example. So if we were, if we wanted to actually do this with our specific kind of taxi data set, we could actually do that. We would specify a function that loads this data frame with pandas, and then you could actually kind of run this, and this would just, load one thing. This is going to be a delayed function, right? So it's not actually going to execute. But then I can go through for each of my files, call this function, and then I'll get back this kind of delayed object. Now, this is not the way that we're not going to use this data frame for the rest of the exercise because Dask has a higher level kind of read CSV library. But this is the idea here is to illustrate like if you had some other messier data that you might need to do, because we often find that clients have to drop down into this kind of delayed interface and clean things up, and then you can work with a data frame later on. And so see that now only gave me 12 partitions, and that's why it's a bit slower, because the read CSV from Dask will be able to chunk things up a bit better. Okay, cool. So when we get to the exploratory analysis section, I can now run this describe in the same exact way that I ran it with pandas, right? Might take a couple more seconds only because this is a much larger data set, but again, I can watch my Dask graph now and I can watch things happen. So now this is really cool because a describe is calling all kinds of different functions, right? Sum, median, min, max, quartiles, and all of those things. You can actually see all of the individual functions that are executing. A lot of them in parallel, a lot of them have to wait. So when you're looking at these colors on the Dask dashboard, they will correspond to all the different functions. So let me go ahead and run that again one more time. You can see now that like purple is this chunking, the blue is like read CSV, and all different things happening. And so those colors will just kind of correspond to those functions. The red is really important because the red is actually when data transfer or shuffling is happening. So in this case, one node or worker needed to send data to a different worker. And that's where you can see sometimes things are pausing. So the reason that that's red is because that takes a long time. I/O between machines over a network is a lot slower than like communicating within RAM of a single computer. So that's why those are kind of red like that. But you could even click through into some of these things and then get more details about all the specific things that are happening if you really wanted to look at the specific profiles. Okay, so I have an exercise here for, and maybe you already went through down to this if you were kind of, jumping ahead a bit, but kind of play around with this data frame. Like you can use this the same way that you would use any pandas data frame, more or less. Like the pandas API is a lot more, it's a lot bigger than what Dask supports, but the things that Dask supports, the API is very similar or exactly the same as pandas. So I would encourage you to go in here and play around with it and do some exploratory analysis. Just do things that you would normally do in your everyday life with the pandas data frame, and you can add more cells and do whatever. I'll put a couple minutes on the clock here because I really want you to like get some experience doing this yourself, hands-on, and you might run into problems, but that's the whole point. So if you run into any issues, feel free to unmute and say so, or post something in the chat, but I want you to really just get your hands dirty with this data frame. So I'll put 2 minutes on the clock here for you to play around. Okay, cool. Well, hopefully we've had some time to play around. There's actually no right answer here, but the idea was to kind of try it, maybe run into things. I actually didn't plan this, so I'm going to try to like play around with it myself. Let's see if I want to look at my data frame. Oh yeah, that's right. So I can do things like, let's see, seeing all my columns. Let's say I wanted to see the unique values of vendor ID. I could say like vendor ID value counts. But again, it's lazy evaluation. It's not executing. So I have to put .compute at the end here. And good. Okay. That only worked because I knew that that column only had a few values. If that column had like 100,000 values, that would not be a fun experience. But so yeah, so that's the same type of stuff. You can do group bys, you can do aggregations, like you can add new columns, right? So if I wanted to say like taxi new call, I could just do like taxi vendor ID. Let's see, like times 3, just doesn't really make a lot of sense. But then if I look at this and preview it, now I'll have this new column here. So again, works very similar in the same way you would use pandas. Okay, so that's where we're gonna get into a little bit of that now. And this is the feature engineering part, and then we're finally gonna get to the machine learning. But right, just like any other data science pipeline, we got to do all this stuff first. So these are the columns that we're specifying our feature names and then our label. This is copied from the other notebook. Another exercise, keeping you on your toes. Go copy over this prep.df function that we created from the single node notebook, and then go ahead and try to apply it to this taxi data frame. So hopefully you've played around a bit with the Dask data frame API. It looks like pandas, but see if you can copy over those contents and then also apply it to the function and see if you need to make any changes or if Dask complains about anything. But at the end of the day, I want to have this taxi feet object to be a data frame where this prep.df was called on it. So I'm going to already give you a little cheat of that second part. Basically, I want to be able to call prep.df on my original taxi data frame and then store it in this new thing and then preview it. But I want you to go and try to fill in this function and see if you can do that. I'll put a couple of minutes on the clock again for that part. All right, time's up. So hopefully you found that function, and it's actually sort of a trick question. The function is exactly the same. So that's one of the testaments to show that this Dask data frame is really built with pandas in mind, is that you could actually have just exactly copied this function as is and then run it through. So like I said, there are going to be things that have some differences, but in this case, we just wrote some feature pre-processing, and it's exactly the same way that we would do it in pandas. If we get a preview by calling head, it'll actually execute. Again, it doesn't execute this whole thing, but it'll execute that pre-processing on a few records here just to show you the preview of what it would be. So that's pretty much most of what we're going to cover as far as like data processing. Really, the data frame, the key points here is the data frame API and then also the delayed API in case you have messier data. So now we're going to jump over to the next notebook, which is actually finally getting to training our models. So we'll go ahead and open notebook 5. And so what, again, because we're in a new notebook, it's in a new session, you have to run some of that setup stuff. So instead of having you copy and paste all those things over again, we have this setup.py file, which loads up your cluster and it'll wait for your machines. It'll load up a data frame and then it'll execute this taxi. So essentially we're getting to the final point that we were in on notebook number 4 with a taxi feet data frame that has already been, where the prepping function has already been executed on it. So if you go ahead and run that setup, it'll take a couple seconds, right? Because it has to run all this stuff. It does the same output. But then at the end of the day, we have these two objects from their client and taxi feet. And then go ahead and, so this is something we didn't try yet, actually. So if you look at the other the script, it's just calling this function, right? So it's still doing this kind of like lazy evaluation. So what I want you to do is go back into some of our Dask reference and persist this data frame. So that way, any future operations that we run on it are really fast, and you can go ahead and block until it's finished persisting. And you can reference our previous notebook if you need some help with that. I'll put 1 minute on the clock for this one. Okay, so hopefully you've gotten that. I'm going to go ahead and kick this off so that way I can do that. So this is calling our persist function. So in this case, now if you go back to the dashboard, you'll see that it's running all of my read CSVs essentially. And it's doing more than that, right? Because I called all of the pre-processing stuff. So it's going to be reading CSVs. It's going to be executing, creating all those new columns that I decided to execute. And then it's going to load all this stuff into memory. So now I'm seeing I'm getting more memory here. And I'm actually not using the memory efficiently because I left my other notebook up and running. If you were to kill the kernel on your notebook number 4, it'll free up some of the memory on your cluster. But the cluster is big enough to handle all this for now. Okay, and so then the wait function is essentially blocking our client until it's done. So it took about 40 seconds to actually load all that data across the clusters. Okay, now we're getting into some scikit-learn territory. And similar with the Dask data frame and pandas, there's a Dask ML library that looks and feels a lot like scikit-learn. And this train test split function, we use this in notebook number 2 if you need to reference how that function is called if you're not familiar with using it. But go ahead and see now it's imported exactly the same way, except now we're using Dask ML instead of sklearn. So go ahead and try to fill in the parameters here. I know this is one of those things where I always have to Google like what the order is of the train test X, Y every time. So it's okay if you copy it or if you cheat on this one. I won't hold it against you. All right, so I'm just gonna go ahead and cheat on that one. So in this case, I'm just grabbing my features and my label for the X and Y, and then I'm giving it a 30% test size, and then I always wanna use the meaning of life for my random state here. Okay, and so you notice those lengths take a couple seconds because again, back to the thing we keep talking about is lazy evaluation. So now it didn't take forever because it didn't have to read the CSV files again because we persisted up above. But then, so now if I call this describe, it's actually executing my train test split again, and then it's going to give me back my results. But now we can see all of our different things here. Okay, so let's actually train a model. We finally gotten to the point of training a model. And what I want you to do actually is because this model, this linear regression we're running is going to take like 5-7 minutes to run. I want you to go ahead and execute these cells. So, and then I'll explain them in a second. So run this cell, the pipeline cell. Run these next 2. Just don't read it for now. Execute this persist. Oh, actually, there's an exercise here. Sorry, I'm going to jump ahead for the exercise. So go ahead and just like click the ellipsis when you get to the fitting, because I want you to trigger the linear regression fitting because that's going to take a few minutes. But you'll see the kind of like dashboard start to light up now because it's just doing all the things that linear regression might want to do. But kick that off, let that run, and then we're going to come back to the top and I'll explain everything. Okay. So this chunk looks a lot like scikit-learn, right? We're even still using a scikit-learn pipeline because the pipeline object itself, you're not really dealing with big data there. That is just like an orchestration thing if I want to hook up different things. So Dask will actually interact really nicely and play really well with scikit-learn. But all of the other stuff requires some data processing. So I don't want to use the scikit-learn classes because those only operate on a single core. In this case, then I'm going to import the Dask ML stuff. So Dask ML here is a little bit different. Linear regression is its own specific object because it does like generalized linear models just because of the way of having to do like distributed computations. Scikit-learn itself has like elastic net and like lasso and ridge and like linear regressions and all those different things. But in this case, I can call the scalar, which is from the Dask ML, and then I get a pipeline the same. I get essentially a scikit-learn pipeline. But in this case now, oh, I already ran that. Oops. So anyway, I get a scikit-learn pipeline. So this is one little bit of a nuance to this specific Dask ML linear regression class. It currently requires array inputs instead of data frame inputs. And so in this case, we need to convert the data frames that we got from our train test split because we started off with a data frame into an array. And I don't have a whole lot of time to fully explain like Dask arrays because the general concept is that a Dask array is a collection of a bunch of NumPy arrays the same way that a Dask data frame is a collection of a bunch of pandas data frames. But there are a couple little nuances here and there just because of the fact that you're running in parallel. We can cover that in kind of some future sessions, but essentially if instead of, you can just call this function to convert your data frame to a Dask array. With pandas, you could call .values, and that would actually give you the array as well. But Dask has to do some computations about the chunk sizes of the different arrays inside of it. So you will need to call this specific function. Yeah, and then in this case, our train test split we did after we persisted. So I don't want my linear regression, when Dask starts to run a linear regression, to go back and redoing train test split in all of its different iterations. So in this case, I want to persist again. And what's cool is that the Dask package also has this dask.persist function where you can give it a bunch of different objects to persist at the same time. And this is a lot. So the other way that you could do this is like if you did like xtrain array.persist, right? And then I can do xtest.persist. And that would work just fine. It would still happen and it would work. But when you do Dask persist like this and then pass in a bunch of different objects, Dask actually knows that some of these objects are sharing computations. So it'll actually execute a little bit faster, because if I called persist individually, it would have to go back, do the split, come back, persist. And then I get to this test, it'll go back, do the split, persist again. In this case, all of these are being derived from the same split function. So Dask will know, oh, I can optimize this and I can split it once and then persist all of them individually. So there's just a little bit of nuance to how you could use this Dask persist function. But again, and then I'm just going to wait for one of them, because if one's done, the rest are going to be done. These are called them pretty much at the same time. And then we went to fitting our model. And so again, spoiler, I didn't let you do the exercise, but if you called lr.fit the same way that you would with scikit-learn, you would pass it your x and y, and then it'll fit a model. So in this case, it's still running, it's doing its thing. You can go look at the graph of tasks. If it's really big, sometimes it has trouble loading it. But yeah, so you can see kind of like which things are in memory and running. Yeah, so there's a lot of tasks here. So this is going to be a lot going on here. And actually, I think it doesn't like me anymore. Okay, so this will just take a couple more minutes to finish up, but I know this task graph is like almost too big now for this page. It doesn't like this anymore. Chrome is freaking out. Okay, let me open up my dashboard again. Okay, here we go. So this is just because this model is kind of iterative, right? So it's just going to keep doing its thing. It's going to keep doing its thing until it's done. But we can see we've kind of ate up a bunch of RAM and it's processing, and it's really fun to just watch the colors. Sometimes I'm just like, oh, this is cool. Okay, so that'll take a couple more minutes to finish, and then we could just do the same things that we would do with scikit-learn. I can, now that I have a trained model, I can call predict with my test set and then do a mean squared error. So in this case, I want root mean squared error. So then we'll put in the squared equals false here, and then we'll get our result. So it's going to be very bad, again, because I didn't create the best features. Okay, cool. Well, we're going to go ahead and keep going forward. This is actually going to be the last section in this workshop. So thank you all for following along here. The last piece I want to show you is slightly a teaser, because there's a lot of things to consider when you're thinking about XGBoost and doing it in parallel. You can even run XGBoost on GPUs with Dask. And so there's like a lot of stuff there. So we're working on another workshop where we'll do like a deep dive into XGBoost. If any of you saw last week or the week before, we did a webinar with Mike McCarty from Capital One, where they use XGBoost and Dask and GPUs in production there, and they were able to get like really, really fast speed ups and get better models because they were using these tools. You can go to our Saturn website if you want to go ahead and watch that. All the events are on there and the recording is up. It was a really cool thing. Mike showed a demo of within Saturn of like training an XGBoost model across multiple GPUs. And then doing like a grid search with like a bunch of different things, which would have normally taken forever, but because it's running on a GPU, it was like way faster. So this is just, again, a quick teaser. And if you notice some of that start script stuff that I talked about, there's a little bit of history here, and it's that there used to be a package called Dask-XGBoost, which was like a separate thing bridging Dask and XGBoost together. But now the native XGBoost package actually has a Dask submodule where it'll use Dask and connect to your cluster like automatically. So now you don't have to install another separate package. You can just use the regular XGBoost package. And so that's another testament to the fact that Dask was built for the PyData world and built to integrate with all of these packages. It serves at the core for a lot of different packages within the Python ecosystem. So you can use it itself, but you can also connect it with things, and it becomes really powerful that way. Oh, okay, I killed enough time to where the logistic regression finished. So we saw that took 7 minutes, and then our mean square error is that. So back to the XGBoost. That's the only reason we have this start script. Again, probably in just a couple of weeks, we're going to have the image updated to where this start script won't be necessary, and we'll be using the latest XGBoost package. But I did want to at least have this ready for you and show it to you here. So you can go ahead and run these. This is actually going to be pretty quick. I'm only doing a max depth of 5 and just 100 estimators. But if you were to try to run this on a single machine, first of all, it's a lot of data, so it's going to take a while. And XGBoost is pretty process and memory intensive. So this would actually, I mean, you can go ahead and try it if you want to on the single machine with the regular XGBoost package. It would take forever. But this is really cool because now this is actually executing in parallel across the cluster. So under the hood, if you're curious, this XGBoost actually has this kind of like parallel concept of being able to use multiple workers. And it's actually using Dask as the XGBoost worker. So it's kind of like bridging the two things together. And because Dask is already orchestrating a cluster, XGBoost is kind of hooking into there and then utilizing the workers in the Dask cluster as XGBoost workers. So if you actually go over to the status page, it's not quite as exciting as the linear regression model because a lot of this work is happening inside of XGBoost. So, oh, and then I think I already finished training, but let me go back to the training. And so in this case, all of the XGBoost logic is happening inside of this dispatched train function. It's not happening on like individual functions that are being exposed to Dask. So that's the one thing. So just that's the reason why you're not seeing like a bunch of pretty colors flying around. But you'll be able to click on this workers tab and you see that the workers are definitely busy processing and doing things. So they're definitely training a model here. It's just because it's inside XGBoost. And in this case, I got a little bit better than I got with my linear regression. This is probably, again, just because the features are terrible. And if you wanted to include more estimators or play around with learning rates and such, you could totally do that. And this should finish in just a second, but this model only took about a minute to train. And that's pretty good on a full year of the taxi data. Like I said, there's a lot more with XGBoost, but I just wanted to at least show you that that's possible, show you like yet another place where Dask integrates with really tried and true open source packages. But that's pretty much it for the workshop. I have a discussion tab here, just kind of reviewing some of the concepts that we went through. You can kind of read that on your own time. But if you have any more questions, definitely let me know here. Otherwise, we can probably wrap it up. Let's see. Let me put this last thing here. So that's the workshop. Thank you again for joining. Thanks everybody for trying it out. You have your accounts to Saturn Cloud Hosted. You can continue to use this. You can run this project again. You can run some other examples that are on our website or create your own projects and start doing your own things. If you have more questions, you're on our community Slack, or you can just shoot us an email here or even send us a tweet. Tell us what you liked about the workshop. Feel free to tag me and Saturn in it. Tell us if you loved it. Tell us if you hated it. Tell us what we can add, things that you might want to see in the future with Dask, maybe with GPUs and with some other things. And as always, if you want to keep up to date with what we're doing, go to saturncloud.io and sign up for our newsletter and all that good stuff. But thank you all for joining, and I can stick around for just a couple more minutes if you have questions, but otherwise, happy holidays and enjoy the rest of your day.